This question is, suppose you have a sequence called Bn, and it's given that the limit of Bn as n approaches infinity is L, where L is not 0. Which of the following statements must always be true when n is large enough? Option A. The absolute value of Bn is greater than 1/3 the absolute value of L. Option B. The absolute value of Bn is less than 1/3 the absolute value of L. Option C. Bn is less than L plus 1 over n. Option D. Bn is greater than L minus 1 over n. Step 1 is to understanding what it means when the limit of Bn equals L. This means that as n gets bigger and bigger, the numbers in the sequence Bn get closer and closer to L. In formal language, we say, for any small number you choose, let's call it epsilon, there will be a point in the sequence beyond which all the values of Bn stay within that epsilon distance from L. This gives us powerful control over how close Bn must be to L once n is large. Step 2 is to let's look at option A. Option A says, the absolute value of Bn is greater than 1/3 the absolute value of L. To check this, let's use a classic trick. Choose the small number epsilon to be exactly 1/3 of the absolute value of L. Once n is large enough, the distance between Bn and L is less than this epsilon. That means Bn stays inside a narrow band around L. There's a useful inequality in this situation. The difference between the absolute value of Bn and the absolute value of L is less than the difference between Bn and L. That tells us the absolute value of Bn must be greater than the absolute value of L minus epsilon. Now, since we chose epsilon to be 1/3 the absolute value of L, subtracting that from the absolute value of L gives 2/3 of the absolute value of L. So the absolute value of Bn must be greater than 2/3 of the absolute value of L. And of course, 2/3 is bigger than 1/3. So the absolute value of Bn is definitely greater than 1/3 of the absolute value of L when n is large enough. So option A is always true. Step 3 is to check option B. This says the absolute value of Bn is less than 1/3 the absolute value of L. But we just saw that for large n, the absolute value of Bn is greater than 2/3 the absolute value of L. So this statement can't be true. Option B is false. Step 4 is to check option C. This one says that Bn is less than L plus 1 over n. Let's test that with an example. Suppose Bn equals L plus 1 divided by 2n. That kind of sequence still approaches L, so it satisfies the condition. But 1 divided by 2n is less than 1 divided by n, which means L plus 1 over 2n is still greater than L plus 1 over n. So in that example, Bn would be greater than L plus 1 over n, not less. So option C is not always true. Step 5 is to check option D. This one says that Bn is greater than L minus 1 over n. Let's flip the previous idea. Suppose Bn equals L minus 1 divided by 2n. Again, this sequence still converges to L. But now, Bn is actually less than L minus 1 over n, because 1 over 2n is smaller than 1 over n. So in that example, option D also fails. Option D is not always true either. Final answer is option A. The only statement that must always be true when n is large enough is the absolute value of Bn is greater than 1/3 the absolute value of L. Here, as quick tip, if a sequence approaches a non-zero limit, its terms stay close to that limit, and so their absolute values also stay close to the absolute value of the limit. A smart move is to pick epsilon as a nice fraction of a limit, like 1/2 or 1/3 of the absolute value of L, to simplify things. Use the trick. The difference between absolute values is smaller than the actual difference between numbers. That helps you estimate bounds on absolute values. To test if a statement is always true, try to break it using a small adjustment to a convergent sequence. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel and turn on the notification bell. Press the like button. Thank you so much.